Today we are going to discuss the fourth primitive affine transform, which is called scaling. And let's look at this example to understand scaling. For I equals 0 to n, y of 2 into I equals z of 2 into I. So we are basically updating every alternate element and also reading every alternate element in z. And then for j equals 0 to 2 into n, j plus plus xj equals yj. Here we are looking at each and every element of j in of y in a sequential order. So you can see that there is a read after write dependency on y, and so we want to capture this. And if I was to draw this diagrammatically, then crosses are S1 and the circles are S2. So these are all the iterations of S1 from 0 to n. These are all the crosses, and then these are all the iterations. The circles are all the iterations from 0 to 2n. So for example, j equals 0, j equals 1, j equals 2, j equals 3, and so on till 2n. Here the crosses are for I equals 0, I equals 1, and so on. Now, when is there a dependency? Well, whenever y of 2 into I equals y of j. In other words, whenever 2 into I equals j. And so for I equals 0, so this is 0. I equals 0. So at I equals 0, we have an edge from I equals 0 to j equals 0. So this is j equals 0. Then we have an edge from I equals 1 to j equals 2, because at I equals 1, I'm accessing y2, and I'm accessing y2 at j equals 2. So I have an edge from I equals 1 to j equals 2. Similarly, I have an edge from I equals 2 to j equals 4, and so on. And now I want to basically, transform this program so that the reuse distance is reduced, and and also if it was a parallel machine, the outer loop becomes parallel. And so I'm going to use my same old space partitioning constraints formulation. And the first thing I'm going to do in doing this is basically represent the program in an affine way, in an affine representation. And so S1, there are two statements, S1 and S2. The iteration space of S1 is from 0 to n, both included, and the iteration space of S2 is from 0 to 2 into n. Now I basically look at the data dependencies. So the data dependencies are basically whenever, so I look at all possible pairs, and the only data dependency I see is between y of 2 into I and y of j. Right, and so basically there's a data dependency if 2 into I equals j. And so whenever 2 into I equals j, it must be true that the two iterations I and j are mapped to the same processor through our affine function that maps iterations to processor space. So in other words, p of I should be equal to p of j whenever 2 into I equals j. This forms our space partitioning constraints. Capital Fi plus small f equals capital F prime I prime plus small f prime. That's boiling down to 2 into I plus j equals j. And then whenever this is true, then it must be true that C1 I1 plus Ci plus small c equals C prime I prime plus small c prime. And that basically gives me Pi equals Pj. And I want the maximum rank solution for P. And it turns out that the maximum rank solution is just the rank of the iteration space itself, where I say P equals 2 into I and T equals j for S2. Right? So for S1, I have the find function which maps every iteration to a processor ID that's twice the iteration count. So for example, it maps iteration 0 to 0, iteration 1 to 2, iteration 2 to 4, and so on. Whereas the second affine function from iteration space to processor space is just the identity function. So iteration 0 maps to 0, 1 maps to 1, 2 maps to 2, and so on. Now with this, this is a maximum rank solution to the space partitioning constraints for finding synchronization free parallelism. And now my job is to basically, using this solution, this maximum rank solution, identify the generated code or generate the code. And this is my naive code generation. Basically, I have an outer loop on P, the lower bound on P based on this mapping, and looking at the lower bound and upper bound of J, I get the lower bound of P is just 0, because that's also the lower bound of I and J, and P equals 2I and P equals J. So 2 into 0 is 0 and 0 is just 0, so lower bound is 0. And upper bound is 2 into n, because it's coming from p equals 2i and i's upper bound is n, so that gives me 2n, and also p equals j and j's upper bound is 2n. So it so happens, this is a very simplified example, and so happens in the simplified example that both the statements upper bound and lower bound are identical. So both of them basically give me, the lower bound is 0 and upper bound is 2 into n. Basically the lower bound and upper bound are identical for both S1 and S2. And then I just paste the original program as it is, alright. So I just paste the original program, except that I predicate S1 and S2 using the mapping function that I have. So for example, I have the first loop is for I equals 0 to n, I plus plus, and this is S1, y2 into I equals z2 into I, except that I predicate it with if 2 into I equals p. So only execute if I'm on the correct processor. Similarly, the second loop for j equals 0, j is less than equal to 2 into n, j plus plus. Once again, I have S2, which is xj equals yj, but predicate it with if j equals p. So this is my naive code generation algorithm, but we know that the naive algorithm is not generating a very tight code. So the next thing we do is tightening of the loop bounds, also called elimination of the empty iterations. So we can see that on this loop, there is only one value that it executes for I, which is basically the value whenever 2 into I equals p. So I could have just said that whenever 2 into I equals p, only then execute it. When will 2 into I equal p for I equals 0 to n? At p equals 0, I equals 0 would be the only iteration that executes. Let's look at what happens at p equals 1. At p equals 1, I equals 0 will not give me 2 into I equals p. I equals 1 will not give me 2 into I equals p, because 2 into 1 is 2, whereas p was 1. And similarly, I equals 2, 3, 4, 5 is not going to give me 2 into I equals p. So this, first of all, there are at most one iterations of the inner body of this first loop that get executed, and exactly one get executed when p was an even number. So for example, 0 when p was 0, when p was 2, when p was 4, and so on. And no iteration gets executed when p was an odd number. All right. So this kind of simplification, we can codify them as some kind of pattern matching rules to figure out, how to simplify this fact that there's only one iteration. I mean, the first thing I would probably do here is just do minimum and maximum analysis to say, okay, starts from minimum of p and maximum of so minimum of p by 2 and maximum of p by 2, or something like that. And basically based on that, I'd be able to say that, okay, there's only at most one iteration that gets executed, but only for some values of those that range am I going to actually even execute a single iteration. So I can even further simplify this to basically say whenever p is even, only then execute this statement, and for that, whenever p is even, it must be true that I equals p by 2. All right, and then I can just substitute p by 2 for I for that case. Similarly, if I look at the second loop, it's for j equals 0 to 2 into n, j plus plus. If j equals p, xj equals yj. Now, in this case, it's very easy to see that only one of the iterations when j equals p is going to execute. So I can just replace this whole loop with just saying if j equals p, and in fact I can just replace if j equals p, but remove it and then instead say xp, because I'm iterating over all possible, so I just set j to p and then just use xj equals yj, and then I can do copy propagation, just say xp equals yp. And so finally in my code generation, this is the kind of code I get. For p equals 0 to 2n, if p mod 2 equals 0, then xyp equals zp, and then also I say xp equals yp. Alright, and this is the transformed code that I get using my formulation of space partitioning constraints for synchronization free parallelism. Notice that if it was a parallel machine, then I could have executed the outer loop on 2 into n different processors, because each of the iterations of the outer loop are independent with respect to each other. If I was to draw the diagram for this particular transformation, recall that the original program looked something like this. I have n iterations of S1 and 2 into n iterations of S2, and my dependency edges look something like this. Whereas in my new transform program, I have 2 into n iterations overall, of which only on the even values of this iteration space S1 executes, and on all iterations of this iteration space, S2 executes. But the important thing is that the reuse distance has been significantly reduced. All these lines, all these dependency edges are now vertical, which means that they belong to the, if there's a dependency, they belong to the same iteration. And this is exactly what the space partitioning constraints formulate and aim to, and this is the kind of solution that they aim to obtain.